Web3 off. Jen?
Hello.
We have the co-founder of Automata Network, Chua.
Hello.
And hitting the stage again, Enrico.
Okay, hi everyone again. If you recall, I'm Enrico, researcher at PSC. And today I'm glad to moderate this panel with Guy, Zen, and Zeng. The topic is a discussion on TE, MPC, and FHE. And without further ado, I will let the speakers introduce themselves, introduce what is their company, and I will also ask them to speak about their company without focusing too much on the technology, but just trying to get what's the value that your company is offering. Maybe Guy, you want to start?
Sure. Thanks for moderating another session, and we're very excited to be here. I'm Guy Tzchaki. I'm the CEO of Phoenix. Phoenix is an L2 and coprocessor that utilizes fully homomorphic encryption to solve one of the problems that we believe is the key problems to be solved in the next couple of years, which is the lack of data confidentiality on different blockchains. So I'm not going to talk yet about FHE. I will in a minute, but I want to state that previous to my role as Phoenix, I used to work at Intel, and I led fully homomorphic encryption initiatives at Intel. As a side story, I also worked a little bit on the Olympic Games, and I was at the same stadium exactly 3 years ago during the Tokyo 2021 Games, so it's kind of a closure of a loop for me. But from my standpoint, we're at a position in time which is quite unique. We think about the Ethereum ecosystem. The key challenges that we're facing so far, which were scalability and high cost, are mostly solved. Yes, there is a lot to be done there, but they're not a burning problem anymore. And the fact that we have everything which is public is literally like a blocking factor that should be solved. And we're going to talk through this panel about how we are planning to do that using fully homomorphic encryption.
Cool. Hey guys, I'm Zen. I'm one of the co-founders of Web3 Off, and what we do is, you know those login boxes that you see on certain Web3 applications, the ones with like email password or Google login or so on and so forth? We power the bulk of applications in Web3 that have that login box. We're behind the scenes, the key management and authentication provider for over 800 live applications in Web3. Some specifically in Japan include, I think, Double Jump Tokyo. Square Enix built the NFT platform on Web3 Off. Let's see, My Crypto Heroes, a couple of others here and there. And we have about 20 million users across a month across all of these different applications. We've been around for a while, so we're the largest player in the space as well. And yeah, I mean, that's more or less what we do.
Nice. Hi, everyone. My name is Zheng Leong. I'm one of the co-founders for Automata Network. So what do? We kind of like, we want to extend machine trust into the entire Web3 ecosystem. So you can think of it as like each of us, we are carrying like a mobile device with us, like be it your iPhone or your Android phone, and even your DSLR cameras and stuff like that. And in each of these machine, what if we can actually give a kind of like identity, or we can tell if this device that you are using is trustworthy, or it's a genuine device, it's an authentic device. And from there, we can have things like provenance of data, or like integrity of computation and stuff like that. So, and we want to achieve it through this process called attestation. I'm pretty sure during the course of the panel, there will be some interesting discussions, and yeah.
Okay, so the next question is about like the technology that you are advocating for. So maybe this time we can start with Zen, that is going to advocate for MPC during this panel.
Yeah, so I mean, just to be clear, Web3Auth doesn't just use MPC. We use MPC plus account abstraction and a couple of other things in our stack. But MPC is definitely one of the more prominent ones. MPC stands for multi-party computation. And it's been a field of research that's been going on for decades at this point in time. Before crypto kind of popularized it in a certain way, it was more used for privacy use cases as well as analytics and data hiding use cases. But crypto really popularized MPC in its use for key management. In particular, everybody, in order to interact with the blockchain, we all need a public-private key pair. And this public-private key pair is very similar to a username password set. What MPC essentially does when it applied to this specific use case is it allows you to split up the password into multiple different parts and store it on different locations that you might want to use. So it's kind of like 2FA, but for crypto.
Okay, so I guess I'll be advocating for TEs. Similar to what Jen said, like at Automata, we don't just use TEs. We actually use it in conjunction with things like ZK proofs and MPCs. So, I mean, why use TEs then, right, if you are using all these other cryptographic primitives? The thing about TEs is you can imagine TE as like a kind of special spell that you can cast. Like each of your machine, there's this magical seal that is embedded in your machine, and then with the right incantation, you can create this shield. And within the shield, no one can see what you're doing. And whatever that you want to do within this like magical shield, it will be done. And you can get guarantees, cryptographic guarantees for it. And through this process, we can actually make use of TEs to help augment some of the other cryptographic processes like MPC in terms of ensuring collusion resistance, or say ZK proof as an alternate proof system for the succinct proofs that's generated by ZK systems. So, and one of the additional kind of like properties that TE has that a lot of other cryptographic primitives don't is actually the ability to delegate trust to a particular third party or external device. Yeah, so.
Perfect. So it's my turn. Before I start talking about FHE, if it's okay, I just want to ask, like, for a show of hands, how many people here heard of FHE or familiar with FHE? Okay, I do see quite a lot of hands being shown up. And the reason I've asked this question is that FHE has been discussed, I would say, for many, many years, but it was always considered as like this kind of magic. Because what FHE does, and it allows us to run computation on data while the data is encrypted. I'll say it again, you can run computation on data while the data is encrypted, which sounds a bit of magic because we were always taught that when you encrypt something, it's meaningless. And if you want to operate over that data, you have to decrypt it. You can then compute it with potentially trusted execution environment, but you have to decrypt the data. The magic of FHE is that you don't necessarily need to encrypt the data. You don't necessarily need to decrypt the data in order to compute on it. What you do is that when you encrypt the data, you encrypt it in a way that maintains the mathematical structure of that data, which then gives you the ability to actually compute over that encrypted data, which is quite transformational because now we can take data, put it on chain, and compute over that data. So users can now do confidential transactions where the actual amount of the transaction is encrypted. You can do private voting and private governance where the voting itself is protected. Because, like, I hope people at the audience know it. Today, everything on the blockchain is public. So anything that's not encrypted is visible to basically whoever wants to see it. And FHE's goal is really to change that. Now, the reason we picked over FHE, and I think this is where things may become a bit more interesting, is because I've been working with TEs for many, many years, and I love TEs. I think TEs are great, but I think TEs have a certain limitation, which is that you need to trust somebody. In that case, it can be the hardware manufacturer or the cloud service provider. And if there is an attack on a TEE, the mitigation of that attack becomes very complex. And I would love to hear like the opinion in a minute. FHE actually does the same thing, but it does it through cryptography. So it's lattice-based cryptography, it's quantum safe, and it's actually operating far better than what it was in the past couple of years. There's been significant progression, and it is ready for prime time. And I'll pause here because I'm pretty sure that my TE and MPC colleagues here have a different opinion.
Well, you know, TEs have this reputation of being like broken because there seem to be like so many different attacks on TEs, like key extraction attacks, side channel attacks, even like physical attacks, like through manipulating the voltage that is going into the CPU, you can actually make the CPU behave in a kind of like weird manner. Well, I actually wrote a paper on how we can break Intel SGX to actually extract the secret keys. But the thing is, a lot of these attacks well, they are theoretically possible, but in reality, in order for you to actually perform such an attack, you need either a very long period of time, because side channels typically have a very low kind of like information bandwidth. That means you can only obtain a little bit of information about the key every time you kind of like probe the hardware. So you need to have a lot of access, like unfettered access to the actual CPU or the actual trusted execution environment. And it might take like 2 hours or 3 hours or 4 hours. So you can think of this as, yep, this might be some cons of using a TEE. But at the same time, if you actually have a use case, for example, I have some ephemeral data that is secret for a short period of time, and then it's going to be made public. What kind of use case can that be? Encrypted mempools. Like when the transaction is in the mempool, it's supposed to be private, but once the transaction has been kind of like accepted, then it is, yeah, we can kind of like publish it publicly if what we want is like a public blockchain. So in this case, a TE, kind of like the flaws of the TE won't manifest that much. So that's kind of like number one. How do you work around some of the cons of a TE? The other is on the actual vulnerabilities itself. Like everything is code, including cryptographic libraries. So the reason why these attacks happen for TEs is that there's some implementation mistake in the microcode or in the libraries of the TE. Similarly, such kind of like bugs or vulnerabilities can exist in other cryptographic primitives too. For example, like in ZK proof, the circuits might be under constraint. So you might accept malicious or malformed proof. Or the verifier itself might be buggy, and then you might actually accept a proof from a proof that you shouldn't actually accept. So yeah.
So you talked a lot about you spoke a lot about the technical and theoretical and also practical implementation vulnerabilities of TEs, right? But just to add on to, I think what Guy was trying to hone in on was that TEs, even in the perfect implementation, theoretical as well as actual implementation, TEs are dependent on individual operators or trusted parties to run and then produce outputs on. So just let me give one example, right? Let's say you have a TE that that you're using it for, I don't know, to manage perhaps your wallet or something like that, and it handles encryption and decryption from your wallet so that you can use it. If this TE goes down, it's not if it's broken into. If the person operating this TE decides, just for whatsoever reason, to not operate the TE anymore, you won't be able to get back your wallet.
Yes, but similarly, this is actually the problem of availability. Like, let's say if I put my key into one single operator without any backup, or like I have a hardware wallet, like a ledger, for example, and I didn't actually copy down my recovery, the 24-word recovery code, and I dropped my ledger into the pool, then sadly, that's probably the last time you are going to see your account and whatever assets that is within. But the thing is, you don't have to like store a single copy of the encryption keys in the TE. For example, we can actually combine TEs and MPCs. The TE can just hold a sharded copy of the secrets. And what you have is actually a kind of like a more robust system compared to just using MPC alone, because I mean, MPC gives you the guarantee that each individual operators actually can't see the encryption keys.
So is what you're saying, you know, that MPC is necessary and TEs are optional?
No. Okay. I would actually say that it depends on your use case, and like if your kind of like use case is the absolute security, I would say use everything. If, for example, your use case is like fast gaming, like gaming L2s, or use cases where you need low latency, but in terms of security, you just need to have a certain level of guarantees, then TEs are really suitable for it. It's cheap.
Cool. So I think we've spent a lot of time attacking TEs, right? But we should spend some time talking about FHE. And I think just for, you know, like FHE is actually, FHE and MPC are actually very similar in terms of cryptographic fields. Like one is really built on the other, and you could say it's just one generic umbrella. But for the sake of specificness and this conversation, I think we could define MPC more specifically to its use cases, which are more popularized at this point in time in crypto. So the specific use cases of MPC and, you know, key cryptography, and FHE being a more generalized approach to potentially the utilization of MPC. So I think one of my core, there's so much research being done in ZK fields, which have, there's a lot of effort being put into ZK and into ZK research, into its different circuit systems, into improving the scalability of things and all. FHE will always have threshold assumptions relative to ZK. So why do FHE?
Okay, I love the question. I'll start by maybe giving a little bit of an FHE versus MPC for a minute. When you think about MPC, it's actually quite valuable. It's a computation mechanism, but the key challenge I have with MPC is that it's communication bound. So you can use, and most of what use cases that you see with MPC are use cases of wallets, of the ability to take a key and share it among the user and the custody. But MPC in general is a very hard problem to solve when you start thinking about taking it into a completely decentralized space, because it's communication bound, and the communication, it grows exponentially as you get more and more nodes out there. So I would say MPC is perfect for wallets, and what Web3 author are doing, I think, is really like the best scenario of utilizing MPC, but it's not the right vehicle when you actually want to do computation in a decentralized way on on-chain data. FHE, on the other hand, is what we call computation bound. It's slower than regular computation, but it's computation bound, which means that better hardware produces better results. And what we've learned in the past is when things are dependent on hardware, they typically get solved. Like you can look at even the AI transformation that happened once NVIDIA started like releasing the right GPUs and things started to become very quickly. We see the same thing with FHE. So I would say FHE is definitely slower than others, but it's actually ready for many of the use cases that we see today. It's probably not the right fit for MEV protection. I agree with you there, and TE is maybe the better solution today. But if you think about like 2 or 3 years into the future, this will no longer be a problem. I will agree that the end game for any type of solution will never be just one cryptography. It will be a mix of FHE, MPC, ZK, and TEs in a way where FHE will be the one that would be utilized to run the computation over the encrypted data. MPC will be used to split the network key and protect that so we have a threshold network and potentially even run that inside a TEE. And we'll also have ZK for verifiability. And that's where I would say the end game is.
Right, so we spoke about the attacks on the TE. Actually, I wanted to touch on a type of attack that can happen in FHE networks. So I will ask this question to Guy, and I'm referring about like collusion attacks. So what do I mean by collusion attack is in a FHE network when there are like multiple participants, you know, we need to encrypt something under a common, like a kind of a master public key. And there must be someone owning the decryption key for this master public key. And in many scenarios, this key is kind of shared across a set of nodes. And this, there are like, I think, 2 types of risk. The first risk, of course, is that these parties can just collude with each other and go ahead and start decrypting all the state. But I think the, even a bigger risk is the fact that you as a user, you as a consumer of this application, you cannot really tell that this happened. So I'm wondering how you defend from this type of collusion attack.
So I think the problem that you're describing is not just an FHE problem, it's also an MPC problem, and I'm sure that my friend here would comment on that. And that is literally, I would say maybe it's even more of an MPC problem than an FHE problem, but we will be facing that. And the problem that can happen with several participants either colluding with one another is a problem which is realistic. The way we can do to solve it is by making sure that we run the part of computation inside a TEE to prevent that from actually happening in a malicious way where somebody has access to multiple nodes and then can actually generate that. The other path is that we are making sure that the participants, you require a large amount of participants and you only need a subset of them, but still in a meaningful way, which would make collusion, I would say, maybe realistic, maybe theoretical, and not really realistic. Is literally like where we're aiming to solve that.
So Zen, how do you reply to that?
You're absolutely right in that both FHE as well as MPC inherit threshold assumptions, which basically, for this out there, means that you rely on a T out of N parties, and on that trust assumption that T number of parties don't collude so as to either reconstruct your key, decrypt your information, blah, 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 so on and so forth. I think the way which we approach and try to solve this problem is really on making sure that the participants on the MPC protocol aren't a network and aren't people or individuals which aren't you, right? The way Web3 auth works is actually we split a user's private key pair and we store all of these different things on things that users already own themselves. So this could be their devices, it could be social accounts that they already own, it could be encrypted under passkeys or or other forms of biometric information in which a user has and owns themselves, right? So I think at the end of the day, it's not about so much as like making sure or changing or that the threshold assumptions in itself are wrong. It's just a tool that we use and making sure that the participants and where these cryptographic pieces of shards are held are good places to keep them.
Okay, so I will just add a little bit and then maybe kind of like end off with something about TEs. So the thing about this collusion attacks on FHE is it depends on how the FHE is actually being used. So you can have a situation where I'm the owner of the data, I encrypt the data, and I want to outsource it for some third-party computation. In that case, there won't be any collusion, any possibility of a collusion, because I own the key. The kind of like the third-party server would just operate on totally encrypted data. So this issue kind of like arise because of the utilization of MPC to hold master key for FHE networks. TEs are a great solution for this, but actually, other than TEs, there have been research that is being done, and it's being done now, on how can we actually find out if there is a collusion or not. The main issue here is that T parties can collude, and we don't know which of the T parties or if they actually collude or not. There are some papers that describe a solution where you can identify if the particular decrypted value actually comes from some of the participating parties or not. So this is kind of like an alternate way on how this problem can be addressed. And finally, kind of like back to TEs, right? Just now, Zhen actually mentioned that in order for us to use TEs, we need to trust a particular manufacturer, like be it AMD, Intel, or say ARM. Well, this is the case now, but in the Web3 ecosystem and industry, right, there hasn't been a lack of like hardware companies. Like there's FHE accelerators, there are ZK accelerators. Why can't we have a distributed TE manufacturer? The secrets of the TE can be kind of like embedded as physically unclonable functions. So you can think of it as the secret key of your CPU is actually the silicon itself. And these kinds of like, if it's being implemented properly, this alleviate the issue on whether the secret key can be extracted from the CPU or not. And in terms of like whether this manufacturing process is trustworthy or not, we can kind of like have a, they call it a kind of like choose and cut destructive testing method, where a bunch of us or N manufacturers would manufacture the chips. We come together and then we randomly sample a subset of the chips, and then we destructively analyze if this is indeed what we think it is. So this way we can actually have a kind of like decentralized TE hardware that is built for Web3.
Right. So we are getting close to the end of the panel. I just wanted to give you the opportunity to tell the audience and any builders that might be in the audience that might be interested in start using this technology. What is your advice to let them go home and start building something?
Well, I'll make this one short, but what I want people to get out of this is that data confidentiality, user privacy is important. We need to have that state of mind as we start building applications into the next couple of years. This is a fundamental infrastructure that's needed if we want to really scale blockchains and make them widely adopted. And that's something that whatever cryptography you're going to use, we will get in a much better state than what we have today. So, you know, go research FHE, go research MPC, go research ZK. But I have to say, it's far easier than where it was in the past, and it is very, very practical from a developer standpoint.
Yeah, absolutely. And I think I absolutely agree with everything guys said. You know, this panel was set out that it was like versus, but really all have great use cases, great applications, and great and great practical benefits to the world. I think if you're looking to get started, do reach out. You can talk to us. That would be a great start. But also, there are a lot of different open source libraries out there which do very simple MPC tooling, be it from just simple oblivious transfers or a little higher level, GG20 open source libraries or otherwise. They're quite fun to play with. They're quite practical. Play around with them. I think they're a lot of fun.
I totally agree. So basically, it's not really a matter of FHE versus MPC versus ZK versus TEs, but rather you think of all of this as like tools in your toolbox, and then depending on the problem that you're trying to solve, apply the appropriate tools to the problem. And yeah, things are a lot better now. There are a lot of like small little toy examples that you can play with to experiment using MPC, FHE, or like even TEs. Now with like confidential VMs, using TEs can't be easier because you can just write your normal program and run it inside a confidential VM. So really excited to kind of like be in this junction in time where there's so much development.
Cool. So thanks for listening, and applause for the panelists.
And thanks, Enrico, for the
Thanks, Enrico.